Hi, welcome back to the Earth Science Classroom, looking at the Geomorphology playlist. It's the intro video to this massive, amazingly huge topic within Earth Sciences. And this video is going to look at certain things. So we're going to look at, what is geomorphology? We'll look at the different sections or divisions or components of this very large, over-encompassing umbrella term. We'll look at how it relates to other areas of earth science or physical geography. We're going to look at the, introduce the various case studies and kind of introduce the playlist. This is the kind of like the intro video that's going to discuss what it is, but then later on the playlist, we're going to have multiple videos on each section of geomorphology, the case studies, how to teach it, what to use, what not to use, the labs, activities, and so on and so forth. So this is the intro video. Guys, come and join me. So geomorphology, let's break down the word, because obviously, the different origins of each part of the word is very important to learn. In science, if we break down the word, we can figure out what it means. And occasionally in science, or most times in science, scientists will make these words up that are either very complicated or very convoluted. But if you break them down, they become very simple to understand. So the first part is geo. Well, geo comes from the Latin Greek for earth. Anything geo, like geography, geosciences, is earth related. Okay. Then we have the word morph, which again comes from Latin Greek, which means to change. And we see that a lot with metamorphic rock. It's rock that has been changed through temperature and pressure over time. And then we have ology. Ology, again, the same root, the same origins, Latin and Greek. Ology means the study of. So as you can imagine, it is earth changing, it's studying the earth, the entire planet, its changes, and this will obviously be over time. So we're looking at a absolutely huge over incorporating term that really involves everything to do with earth sciences. Now, the only really thing that it doesn't include would be astronomy, because that is technically not on the earth, but outside the earth, beyond the earth. So astronomy is like the only real subject within the earth sciences or geosciences or physical geography that is not included in geomorphology. However, everything else is. So we can take this very large subject of geomorphology and look at it in the terms of a systems approach, or we look at it in the way of a system, huge machine, a bunch of components, a variety or myriad of parts that all work together to create a system. Now, as we know, this system, this planet we live on, this amazing blue planet, is extremely well balanced, and it is very delicate. You change one thing, there's going to be a resultant product, a shift to something different. Something's going to happen. Now, this could be over time, different location, or different environment. But if you change one thing, there's going to be some outcome that is going to be changed, or there's going to be some sort of chain reaction throughout different parts of the system. and it's very difficult sometimes to visualize or even uh, quantify those changes because of the planet is so large and it occurs over a large area or a large time, or it's so small and minute that we can also not see it or not um, really appreciate the change. So we understand that everything is a massive system, a big, huge system. And if you change things, then there's going to be a result, and the system will be either broken or shifted or changed in some way. Now, this has come around for a long time in the education of Earth sciences and teaching students of how to look at it in this systems approach, because it is a massive planet with millions and millions of different parts working seamlessly together. And to figure out how things work, you first have to figure out and understand how each part works, and then how the part relates to other parts and the interactions and relationships between those parts. And then eventually you get this somewhat idea of how the Earth works. These interactions like certain cycles, like the water cycle, the carbon cycle, the sulfur, phosphorus, nitrogen cycles, they all go between these different spheres, which is a term we introduced in the first one, spheres, and how they all interlink and interrelate. And this causes changes on the surface, which is really what we're looking for in geomorphology, is that change on the surface and what is causing the changes on the surface. So the history of this word, this term, this subject, geomorphology, really has come around since the late 1800s, so 1870 to 1880, that kind of decade, where scientists were starting to investigate different processes, have an idea of the large-scale Earth in terms of the macro essence of this planet. And then one gentleman, McGee, which was 1896, but was kind of coined, and he started it basically in 1888. He then started to really put some clarification on this term and kind of break down what it is. So geomorphology is broken into three divisions. The first division is constitution, which basically is what it's made of. What part we're looking at, and what is the composition, constitution of that part we're looking at in detail. The next one is the configuration. How is it configured in terms of the size and the dimensions of this part of geomorphology? And the third one is going to be mass flow. So in general, how is it changing over time? Over time, which again is, what we're looking at for the change, what's happening on the surface. Now, this keeps saying surface, but I'm looking at the Earth's surface, because that is the main kind of laboratory that we look at. The environment is the Earth's surface, the different types of landforms that we get on the surface. Okay? So as we know, whether you're watching this video or listening to this video in Europe or North America, South America, even on the research basis in Antarctica versus a small village in Norway, or some sort of awesome town in Tokyo or Australia, we know this planet is amazing. This planet has so many different types of terrains, landforms, structures, and we know that it changes over time. Not just our lifetime, our span of 100 years, but over a huge amount of time. Now, these landforms can develop and change over time. They can be more consistent, and we know them as, you know, these beautiful parts of the planet where you go to certain areas, you expect certain landforms. So in terms of like the planet, we get the arid or dry landforms. We get the sand dunes, the sandy deserts. We get the dry grasslands. We get the dry rocky areas, the tundra. We get the volcanic or volcanism areas, which we'll get to later on in the flowchart. So where there's active magma, lava, there's upwelling of asthenospheric magma coming through the surface, or there is heating of the Earth's surface through magmatic material, magma plumes, hot spots, like in Yellowstone, like in the top right over here, Yellowstone. We've got some beautiful Hawaiian Poe lava right there, and a lovely lava fountain. But that volcanism is, again, it's part of that geomorphology topic where you have the creation of new environments. Next, we can look at all of the water kind of environments, the fluvial subjects, the hydrology, the fluvial systems, the different states of water, being obviously, you know, solid with ice, liquid with water, but also you have the difference between freshwater and saltwater, oceanic and terrestrial water bodies. You have the classic river systems, watersheds, catchment areas, different stages of the river, from the head and source of the river down through and meandering through, eventually getting down to the estuaries, the deltas, the part where that river, that fresh water, is going to meet the ocean. You also can involve the groundwater. You can do infiltration, or you can do this water in the soil, water in porous rocks, water as aquifers. So, Ken, this is a very large topic and involves a lot of different components. The ocean itself, with the waves, with currents, with density, and the deep water currents versus surface currents and the wind. You have the coastal region where you have the land right here meeting the ocean, where you're creating, the water is creating different environments. Just want to say down here in this bottom right picture here is the picture of Chapel Porth Beach in Cornwall, England. Now, I grew up in Cornwall, originally from Cornwall, and from a small town called Three Milestone, which is outside of Truro, one of the bigger towns in Cornwall. And this beach is a National Trust beach, so it's a government-run kind of national park kind of beach. It's very pristine, very beautiful, very clean, just pure nature. And this is where I kind of fell in love with earth sciences, geosciences, and obviously pursued my degree in physical geography. And it was just amazing. This rock, actually, we should stand on and look over the Atlantic Ocean. You know, these beautiful high cliffs, beautiful metamorphic igneous rocks, and then obviously the beach at the bottom. But it was just a very magical area to experience when growing up, and really, you know, got me inspired by the Earth and everything that is to do with geomorphology, atmospheric science, all that good stuff. So yeah, water is a huge part of this topic. Another set of landforms we can discuss, obviously, is the mountain regions, the high elevation, the process of orogeny, uplift, whether it's local or regional, over different time scales, like the Himalayan mountains, like the Rockies, like the Alps, like the Andes, these beautiful large mountain ranges, whether they're volcanic or not volcanic, and then obviously how they are eroded and weathered and changed over time. Every mountain range is different sizes, different styles, different peaks, different environments, whether it's snow covered or tundra, or whether it's a hot, arid mountain region, like the Atacama or the Atlas Mountains in Africa. You've got these beautiful mountain ranges of different styles and different types. Then you have the forested regions. Now we know forest comes in different styles based on precipitation and climate, but you get the temperate forest, the tropical forest, you get the cold forest, you get the boreal forest going across all of Europe and Siberia and Russia. You get the different kind of trees and vegetation and ecosystems that basically are spawned from the climate, which again can create these different environments, different landforms, again, under the very large topic of geomorphology. So you can investigate different types of soil, different kinds of vegetation, different kinds of trees, and of course the ecosystems that follow with these different environments. And it all comes down, obviously, to climate as one of the major driving forces, driving mechanisms of these different environments. And lastly, with the combination of climate, water, different erosional agents, you do get some absolutely beautiful, beautiful landforms that are created. Now, you can go to national parks, you go all around different parts of the world, and you see some incredible landforms, all created by weather and erosion, various constructive or destructive mechanisms that create these landforms. You've got Monument Valley on the border of Utah and Arizona. You've got various arches, formations. You've got these amazing natural landforms. The Grand Canyon, for example, just has millions of visitors every year because they want to see that amazing sight of nature right in front. They want to be part of nature. We understand that we are one with nature, that we should preserve and respect the earth, understand the earth and how it forms and how it changes, because we only have this planet. And if we go and destroy it, then of course we'll work without a paddle, basically, and we're in trouble. So that ignorance and moronic behavior of destroying the only planet we have obviously goes without saying. We need to understand the earth, and this is where geomorphology comes in a big way. So I like flowcharts because it kind of gives the overall visualization of the subject. So geomorphology can be broken down into physiography. And it can be it's basically the large areas, large provinces. And it's dictated by climate. It is dictated by vegetation, which again can link back up to climate as a control. It can link up to the soils. It could link up to the different topography, right? How the land is contoured, how the land is, the terrain is over a certain area. You can also look at the bedrock, which again will link up to the soils, link up vegetation, and link up to the intrinsic endogenic processes, the internal processes that will cause either uplift or volcanism. And we can also look at, if we just look at it, also look at the hydrology, which also can link up to more things as well. So the physiography is a large topic in itself, and that's just one part of geomorphology. The next is going to be the superficial processes. What happens on the surface? Okay, so we're looking at mass wasting, the effect of gravity and weight on an area with slope or gradient. We're looking at, again, looking at landforms, so glacier or glacier environments, frozen water. We're looking at ocean systems, oceanography. So in the terms of the interactions, so coastal, so it's interaction of water and land. We're looking at, I said before, the fluvial systems, the rivers, the watersheds, the streams, the brooks, even groundwater can be involved with this as well. We're looking at the active tectonics, the orogeny, the volcanism, hotspots, that kind of stuff. We're also looking at there's a little arrow right here, also looking at the weathering and erosion. So this is a massive topic in terms of different agents. So the weather and erosion, looking at wind, we're looking at the big one, water, we're looking at gravity, and the fourth one, which I like to also include with water, is ice. Right, so we're looking at the weather and erosion, and again, this can be linked up to climate as well. It can link up to hydrology as well. So as you can see, I'm going to build this graphic, this kind of flow chart, flow diagram, and you'll see that everything starts to link up together. So we're looking at also is climate. Climate is a very important, very integral part of geomorphology. And the balance between was it exogenic and endogenic processes. Now, exogenic, that's basically the superficial processes on the surface. Endogenic, that pretty much is the internal processes like the active tectonics. So this one right here is our endogenic. The rest pretty much is going to be exogenic processes we discuss in geomorphology. And the balance between these two, the balance between these two is called mass balance. And it relates to how much is being constructed, which is the active tectonics, right? Plate boundaries, margins, Wilson's cycle, supercontinents, orogeny, okay? The constructive part, which is tectonics, versus the destructive part, which is the exogenic, the weather and erosion, the slow breakdown of these landforms, of these areas to create the landforms, based on all these different things, with the main one being climate. So in terms of timescales, geomorphology works over different timescales, and different parts of each division, let's say fluvial versus glacial versus coastal, they have different timescales. So for us to study this, we need to understand that things happen over different timescales, different locations and environments to create the different landforms and the changes that occur. So micro obviously is the smallest. So in terms of the area it's covering is around or less than 0.25 square kilometers. And this is happening over like a 10-year average lifespan. So over 10 years on average, you're going to see certain changes that occur. Then look at the meso or meso. Now it's obviously 0.25 up to about 100 kilometers. So in terms of the areas, the size of the area is going to increase exponentially up to 100 square kilometers. Again, this happens over 1,000-year average lifespan. So again, we've got this large, this is kind of the easiest one to really quantify, easiest one to see change and to experiment with and to kind of understand. Then to translate that understanding to a much larger scale, much larger area, can be tougher. We've got to use a lot of geologic principles to induce or estimate what's going to happen. Then we get the macro. The macro is looking at a much larger area, so 100 square kilometers up to 1 million square kilometers, which obviously can involve a very large area, could involve multiple climate zones, could multiple elevations, multiple different landforms as a whole, even a whole country. And this is over a much larger timescale of 10 million years. So again, looking at either ancient history, paleogeography, paleo earth sciences, and it's a lot harder to kind of like estimate or find evidence, basically. Then we get the mega. The mega is anything over 1 million square kilometers is mega, and anything over, again, 10 million years. So we're looking at the billion years, giga annum, okay, and we're looking at, you know, very, very large areas, continents, the shields, the cratons, supercontinents, and in terms of eras as well, and eons. So we'll judge your time there. So again, the depth of knowledge is going to decrease as we go towards the mega compared to micro. And again, not only is this a very large subject, but now we're looking at huge amounts of area and time scales to figure out as well. All right, so guys, I hope you enjoyed this intro to geomorphology. We're going to get into much more detailed videos of each section as discussed in the flowchart, and I hope you join us for those videos.